Now we can discuss the conservation of energy of rigid bodies. We can extend our discussion of work energy theorem, which states that work done by all forces acting on the rigid body from outside if you sum them up, work done by all forces, work done by F1 plus work done by F2 and so on plus work done by Fn, all external forces, because internal forces cannot perform any work for the rigid body or on the rigid body. That is the work done by all external forces is equal to this much, will be equal to change in kinetic energy. Work done by the external force, net external forces, the net work done by all external forces acting on the rigid body is equal to change in kinetic energy of the rigid body. And these external forces can be subdivided into two parts: conservative force, non-conservative force. Sum of work done by conservative forces plus non-conservative forces is equal to change in kinetic energy. And if work done by the non-conservative force, such as frictional force, is equal to 0, work done by the conservative force can be written as minus del U. All conservative forces perform work at the expense of the potential energy. Therefore, work done by the conservative forces is equal to negative of the change of the potential energy. Putting this relation, we have minus del U is equal to del K. This gives us del U plus del K will be equal to 0. Therefore, we can conclude that total mechanical energy will not change. In other words, we can say that total mechanical energy remains conserved. So the criteria is, the condition is work done by the non-conservative forces will be equal to 0. That's possible only when either non-conservative forces should be absent, or even though they are present just like static force of friction, it must not perform any work. Then only you can conserve the total mechanical energy of the system. And I can support this statement by some example which states that whenever the non-conservative forces perform 0 work, we can conserve the total mechanical energy of the rigid body. The conservation of energy holds good when the work done by the non-conservative forces will be equal to 0. That is the idea. Let us use this idea to solve some simple examples. Let us take an example. The rolling object, say this is a solid cylinder. It is rolling down the inclined plane of angle of inclination theta with respect to horizontal. This is released from certain height h from the ground level. When it reaches the ground, how to calculate its velocity? Using conservation of energy, we can solve the problem. But first of all, we have to prove that this theorem will hold good for this problem. We have already proved that the force of friction, the static force of friction here, work done by static force of friction is 0. We have already proved it. Normal reaction will perform 0 work, that also we have proved it. Because these two forces act at this point, and this contact point of the rigid body doesn't move in the case of pure rolling. Therefore, these forces do not perform any work in this case. Next is the gravitational force. Gravity acts at the center of mass, and center of mass gets displaced through a distance xa. The angle between the gravitational force, that is mg, and displacement of the point of application of the gravitational force, that is the center of mass, is equal to phi. Let. So the work done by gravity is equal to mg into sc, the angle between these two vectors, that is phi, cos phi. When this is phi, this is theta. Theta plus phi is equal to 90 degree. So phi will be equal to 90 degree minus theta. So cos phi will be equal to sin theta. Substitute cos phi here to get work done by gravity is equal to mg xc sin theta, and let xc is equal to x, mg x sin theta, and x sin theta will be equal to h. We can write mgh. Gravitational force is a conservative force. Non-conservative force doesn't perform any work. Therefore, there is a clear-cut case of conservation of energy. We can conserve the energy, or we can apply work energy theorem, which states that sum of work done by all forces, that is equal to work done by static friction plus work done by the normal reaction plus work done by gravity, that is equal to mgh, and change in kinetic energy, that's equal to, for solid cylinder, the change in kinetic energy will be equal to half m into v square. V is the velocity of the center of mass at this point, 1 plus k square by r square. And for cylinder, solid cylinder, k square by r square will be equal to half. So half mv square into 1 plus half, that is 3 by 4 mv square. The total work done, this is change in kinetic energy. Apply work energy theorem, which states that W is equal to del K. So total work done is mgh, and del K is 3 by 4 mv square. Therefore, the velocity will be equal to 4 by 3 gh, square root of this, answer. This is the process where we used the work energy theorem That the method number 1, work energy theorem. You can use the second method, conservation of energy. Change in kinetic energy plus change in potential energy will be equal to 0. The kinetic energy change will be equal to 3 by 4 mv square. When the center of mass comes down through a height h, the gravitational potential energy will decrease by mgs. Therefore, change in gravitational potential energy will be equal to minus mgs, will be equal to 0, and at last you are getting the same answer. So, this is a clear-cut case of energy conservation principle for pure rolling. Since they work done by the non-conservative force, that is the static frictional force, will perform 0 work, we can conserve the total mechanical energy of the system because gravitational force is a conservative force. Work done by the conservative force is equal to negative of the change in its potential energy. Conservative force does work at the expense of its potential energy. Therefore, the conservation principle of the mechanical energy will hold good for the case of pure rolling if no external force, non-conservative external force will act on it. And even though these forces can be treated as non-conservative forces, they do not perform any work. Therefore, we can conserve the total mechanical energy of the rolling object or the rigid body in this case. In this way, by using the conservation of energy principle, we can solve some more problems. In the next class, we will discuss more elementary problems based upon the conservation of energy principle.